So, let's go. Number 1. The 2 rulebooks that can't both be true. You were promised that physics understands reality. It doesn't. It runs on 2 separate rulebooks, and where they touch, they call each other liars. The first rulebook is general relativity. It says space and time are one smooth fabric, curved and continuous, bending gently around anything with mass. It has never once been caught being wrong. The second rulebook is quantum mechanics. It says the world is grainy, chopped into discrete little packets, and nothing has a definite value until you force it to. It has also never been caught being wrong. Put them in the same room, and they start screaming. Relativity wants a sharp, exact amount of energy at every exact point in space. Quantum mechanics forbids that. The uncertainty principle says the more precisely you pin down where something is, the more its energy smears into a fog. One theory demands a clean number. The other says a clean number is impossible. They cannot both be describing the same universe, and yet they are. It gets stranger. In quantum mechanics, time is a clock on the wall, ticking outside the system, the same for everyone. In relativity, time is part of the fabric itself, stretching and sagging, running slower near a heavy object. So when physicists try to build one theory that contains both, they hit a wall so basic it barely sounds like physics. They can't agree on what time even is. Every attempt to force the two together produces infinities, not big numbers, actual infinities. The math throwing its hands up and refusing to give an answer. For most of a century, the smartest people alive have thrown themselves at this, and the equations keep spitting nonsense back. Here's the part that should bother you. You'd think we could just run an experiment and settle it. We can't. The place where the 2 rulebooks actually collide is unimaginably small. A scale so tiny that compared to a single proton, it's about what that proton is to the entire solar system. No machine we could ever build reaches down there. The referee lives in a stadium we can't enter. So this is where you start. Not with one strange fact about reality, but with the fact that our 2 best descriptions of reality contradict each other at the root, and we have no way to test who's right. And that's the calm part of this video. Number 2. Every choice splits reality. Here's a fix for all that quantum weirdness. It's clean, it's simple, and it costs you everything. Standard quantum mechanics has an ugly extra step. The equation flows along beautifully, describing every possibility at once, and then, the instant you look, it suddenly snaps to a single outcome. Nobody can tell you why. Nobody can tell you when. It's a hand reaching in from outside the math to pick a winner. So a young physicist named Hugh Everett back in 1957 asked a dangerous question. What if you just delete that step? What if the equation never snaps? What if it means exactly what it says? Then every outcome happens. All of them. Every time a particle could go left or right, the universe doesn't choose. It splits. One branch where it went left, one branch where it went right, both fully real, both containing a version of you who saw it happen and thinks that was the only thing that could have. You are splitting right now. Reading this sentence, 1 trillion quantum events are resolving in your body and the air around you, and each one is fanning the world into copies. There's a version of you who stopped watching a second ago. A version who never clicked. They're not ghosts or maybes. In this picture, they're as solid as you are, and you will never, ever reach them. Everett wrote this up as his graduate thesis, and physics ignored it for 20 years. It was too much. But the disturbing thing is nobody could prove it wrong. The math is cleaner without the collapse, not messier. Some of the sharpest physicists alive think this is simply how it is. And it has a hole nobody has plugged. If every outcome happens, why do the odds still work? Why, when the equation says a thing happens 1 time in 4, do you actually see it 1 time in 4? In a universe where everything happens, the very idea of probability starts to melt. And the best minds in the field have been arguing about that gap for decades without closing it. You clicked on this expecting theories about black holes and the edge of space. Instead, the first real casualty is the thing you never thought to question, that there's one of you. That today had one outcome. Maybe it didn't, maybe nothing ever does. Number 3, the hidden waves, steering every particle. Now throw all of that out because there's a completely different reality that fits the exact same data. And in this one, nothing is random at all. It's called pilot wave theory. The idea is older than you'd think, sketched by de Broglie in 1927 and revived by David Bohm in 1952, and it says something almost old-fashioned. Every particle is a real thing, sitting at a real location, at every moment, whether you look or not. No fog, no split, no snap. So why does everything seem so uncertain? Because riding underneath every particle is a wave, a guiding wave, and it steers. The particle is like a surfer carried along the contours of a swell it can't see. You can't measure the particle's exact starting point, so you can't predict where the wave will carry it. And that ignorance, only that, is what looks like randomness. Underneath, it's all clockwork. Fully determined, nothing left to chance. Same predictions as regular quantum mechanics, every single one. There is no experiment in a lab today that can tell you whether you live in the branching universe from a moment ago or this quietly deterministic one where everything was set in motion long ago and simply plays out. There was a beautiful hint that this might be right. Scientists dropped tiny oil droplets onto a vibrating bath of oil, and the droplets started bouncing, surfing on the ripples they made. And they behaved like particles. They fell into neat orbits. They fanned out through a single slit in the patterns quantum things make. For a while, it looked like someone had built a little visible version of hidden reality on a lab bench. Then they ran the real test, the famous double slit, the one experiment that defines quantum weirdness. And the droplets failed. The beautiful analogy fell apart at exactly the moment it mattered. The dream of a simple concrete world hiding under the fog took a hard hit in front of everyone. But here's why this belongs on the list. Pilot wave theory itself was not killed. It still fits. It still cannot be ruled out. Which means you have two complete incompatible pictures of reality on the table, one where you shatter into countless copies, one where you were never anything but a fixed point following a script, and physics cannot tell you which one you're living in. It can only tell you they can't both be true. Number 4. Nothing you do was ever a choice. There's one more escape route from the weirdness, and it's the one physicists mention quietly because it doesn't just rewrite reality, it reaches into your skull. To understand it, you need to know about Bell's theorem. In 1964, John Bell proved something that felt like it closed the case. He showed that no theory where particles carry their answers around locally, tucked inside them, can match what quantum experiments actually do. The particles seem to coordinate across distance in a way nothing local should manage. For 60 years, careful experiments have confirmed it again and again, tighter and tighter. Local common sense reality appears to be dead. Except Bell left one door open. His proof rests on a single assumption so obvious nobody thought to question it. That the experimenter is free to choose what to measure. That the particle doesn't know in advance which knob you're going to turn. Take that away and the whole thing collapses into something called superdeterminism. And it says this: the particle and your choice were correlated from the beginning, not because the particle is psychic, because the entire chain of cause and effect, including every thought that will ever cross your mind, was already threaded together at the birth of the universe. You think you're deciding which button to press? The decision and the particle were the same event, set in motion before there were stars. This isn't fringe. One of its loudest supporters is Gerard 't Hooft, a Nobel laureate. Others, like Sabine Hossenfelder, argue it's the cleanest fix we have because in one stroke it erases the randomness, erases the spooky action, erases the whole measurement problem. Everything becomes local. Everything becomes real. Everything becomes lawful again. You just have to give up the idea that you were ever a free variable in the equation. And here's the part that keeps it on this list instead of in a philosophy seminar. You can't test it. By its very design, superdeterminism can imitate any experiment you run, because it already accounted for the experiment when it set up the universe. It can never be proven, and it can never be ruled out. Some physicists call that a fatal flaw. Others call it the honest truth we're too scared to look at. Either way, sit with the possibility for a second. The sense that you're choosing where to point your attention right now, that might be the most convincing illusion the universe ever ran. And nobody can prove it isn't. Number 5, is the wave function real or just what you know? Step back from all the interpretations for a moment and ask the most basic question there is. The thing at the center of quantum mechanics, the wave function, the object every physicist uses every single day, is it a real physical thing out in the world, or is it just a record of what you happen to know? You'd assume we sorted this out a century ago. We didn't. It is genuinely open, and the two answers describe wildly different universes. If the wave function is real, then this spread out cloud of possibility is an actual object physically present, as real as a rock. Reality itself is smeared and blurry until something forces it to sharpen. If instead the wave function is just knowledge, then the blur was never in the world at all. It was only ever in your head, a bookkeeping tool for your own ignorance, and the real particle underneath had a definite state the whole time. For decades, this looked like a question you could never settle, a matter of taste. Pick the story you like. Then, in 2012, 3 physicists named Pusey, Barrett, and Rudolph proved a theorem that dragged it out of the realm of taste. They showed that if you make one very reasonable assumption that two systems prepared separately have separate, independent realities, then the just knowledge story breaks. It cannot be made to work. You can't have the same underlying reality quietly hiding behind different wave functions, which means if there's any real world under the math at all, the wave function is part of it. The blur is out there. Reality really is smeared until it isn't. Let that sink in, because it's worse than it sounds. It means the fog isn't a limit on what you can know. It's a feature of what exists. The object at the heart of our most successful theory of everything is either a physical thing that behaves like nothing else in the world, or a confession that we don't know what's real underneath. There's no third comfortable option left, and notice what just happened across these 5 theories. We haven't disagreed about some far-off galaxy or some exotic particle. We've failed to agree on what the central symbol in the equation actually refers to. The thing physicists write down millions of times a day. We use it perfectly. We cache its predictions to 11 decimal places. We just don't know what it is. Number 6, nothing has properties. Until you ask the right way. You believe your keys have a location right now, sitting wherever you left them, whether anyone's looking or not. That belief is the thing this next theory takes away. In 1967, 2 mathematicians, Kochen and Specker, proved something that still hasn't been fully absorbed by anyone who hears it. They showed that in the quantum world, a particle's properties don't simply sit there, waiting to be read. The value you get depends on what else you measure at the same time. Think about how strange that is. Ask a particle question A alongside question B, and you get one answer. Ask that exact same question A, but this time alongside a different question C, and question A gives a different answer. The particle didn't change. You changed the company the question was keeping. And the property rearranged itself to fit. It's as if your keys were on the table when you looked for them near the door, but the moment you also glanced at the window, they'd been on the shelf the whole time. Not moved, just never committed to a location until the full question was asked. Physicists have a bloodless word for this: contextuality. The context of the measurement helps decide the outcome. What it really means is that the universe might not keep a complete list of facts about itself, sitting in a drawer, waiting. Some of those facts may not exist until the exact moment you ask, in the exact way you ask. And this isn't a chalkboard fantasy. They've tested it. In 2006 with beams of neutrons. In 2009 with single ions trapped and held in electric fields. Every time, reality behaved exactly as Kochen and Specker said it would. The properties refused to pre-exist. Here's the twist that should unsettle you most. This bizarre feature, this refusal of the world to have definite properties in advance, is not a bug scientists are trying to fix. They're using it. It's becoming one of the ingredients that makes quantum computers powerful. The strangeness pays rent now. So the world you picture, the one where every object quietly holds all its properties at all times, ready for inspection, may simply not be the world you live in. Reality might be more like a conversation than a warehouse. It answers what you ask in the context you ask it and holds nothing extra in reserve, which raises a question you don't want to think about too hard. What's there when nobody's asking anything at all? Number 7. Gravity might be what forces reality to pick. Every theory so far has one thing in common, and it's the thing that should frustrate you. None of them can be tested. We're trading unprovable stories about what the fog means. So here's the one place where reality actually talks back. The idea comes from Roger Penrose and a physicist named Diossi, and it goes after the deepest mystery of all. Why does a spread out possibility ever become a single fact? Their answer is beautiful. Gravity does it. Picture a speck of dust in two places at once, a real quantum superposition. Because it has mass, each version bends the spacetime around it just a little. So now you don't just have the dust in two places, you have two different shapes of spacetime laid over each other, and Penrose's claim is that the universe cannot hold two versions of spacetime steady, the strain is too much. So reality snaps to one, all on its own, no observer required. The heavier the object, the faster it's forced to choose. And this is the moment the whole video turns. Because unlike every idea before it, this one makes a prediction you can actually check. If gravity is yanking these superpositions closed, the process should shake the particles slightly, and shaken charged particles give off a faint whisper of radiation, a specific tiny glow. So you go looking for the glow. They did. Deep underground in Italy, under a mountain of rock to block out every other signal, physicists ran detectors for exactly this whisper. In around 2020 and 2021, they got their answer. The glow wasn't there. Not at the level the simplest version of the theory demanded, which means that clean, elegant version of Penrose's idea is wrong. Reality was measured, and it said no. A deeper detector in a mine in South Dakota tightened the noose further. The plane theory is dead. Only complicated patched-up variants are still breathing. Feel the difference. For 6 theories straight, we've been stuck describing pictures nobody can confirm or deny. Here, finally, the universe let us ask a real question, and it answered. And the answer was that one of our most beautiful ideas about reality is false. That should be a relief, a rare bit of solid ground. Instead, it's the opposite because it tells you these aren't just word games. Some of these theories are testably wrong, which means the others, the untestable ones, aren't safely abstract. They're just the wrong ones we haven't caught yet. Number 8, space itself is knitted from entanglement. Everything you've pictured so far has happened inside space. Particles here, detectors there, distance in between. Now the ground itself gives way because there's a serious idea in physics that space is not the stage at all. It's the show. And it's stitched together out of something stranger than space. The something is entanglement. When two particles are entangled, they share a single fate, no matter how far apart you carry them. Measure one, and the other answers instantly across any distance. Einstein hated it. He called it spooky action at a distance, and he was sure it hid some ordinary explanation. It doesn't. It's real, and it's been confirmed so thoroughly it won a Nobel Prize. In 2013, 2 physicists, Maldacena and Suskind, noticed something that sounds insane and might be true. They proposed that entanglement and wormholes are the same thing, that every pair of entangled particles is connected by a tiny bridge through space-time, too small and too fragile to travel through, but there. 2 things that look completely unrelated, a quantum link and a tunnel through the fabric of reality, might be one phenomenon wearing 2 costumes. And that cracks open a much bigger thought. If the connections between things are made of entanglement, then maybe the space between things is too. Maybe distance itself, the plain fact that 2 objects are far apart, is just a report on how weakly they're entangled. Strongly entangled things are close. Weakly entangled things are far. And the smooth, reliable space you move through every day is knitted thread by thread out of these quantum links. One physicist put it in a way that lingers. Start cutting the entanglement between 2 regions of space, he showed, and the space between them starts to tear apart. Pull out all the entanglement and the distance doesn't just grow. It stops meaning anything. The two regions fall out of each other's universe. Sit with what that implies. The stage you assumed was fundamental, the empty container. Everything happens inside might be a side effect, not the floor of reality, a pattern woven on top of it. And the real substrate underneath, the thing space is made of, is a web of ghostly connections that don't care about distance because they're the thing that invents distance. We can't yet prove it. It's still a conjecture, argued over in equations most people will never see. But the fact that it holds together at all should rearrange something in you. The emptiness between the stars might be the most complicated thing in the universe. Number 9. Reality might have no bottom floor. Here's a comfort you've leaned on your whole life without noticing. The belief that if you keep digging, you eventually hit bottom. That reality has a floor. A smallest thing, a final layer, the fundamental level where the explanations finally stop. This theory says there might be no floor at all. Look at the history of the digging. For a long time, atoms were the bottom. The word itself means uncuttable, the thing you can't break down further. Then we split the atom and found protons and neutrons. So those were the bottom. Then we cracked those open and found quarks. So quarks are the bottom, surely. Except nobody can promise you that. Every single time we've declared a final layer, we've later found a smaller room underneath it. So a real question haunts the edge of physics, and it splits people who think about it for a living. One camp says there has to be a bottom. There must be a fundamental level, some ultimate stuff that everything else is built from. Because without it, what holds the whole tower up? Everything would be resting on something, which rests on something, forever, with nothing at the base to support it. They find that unbearable. The other camp shrugs and says, maybe it's turtles all the way down. Maybe there is no deepest turtle. Layers below layers below layers without end, and the tower supports itself precisely because it never stops. One philosopher who's looked hard at this points out that the demand for a bottom floor rests on almost nothing but gut feeling. We want there to be a final answer. Wanting isn't evidence. And notice, physics has never actually found the floor. Not once. It has only ever found the next layer down. The bedrock everyone assumes is there is a bedrock we have literally never touched. This is quieter than a splitting universe or a collapsing space-time, but in a way it's the most undermining idea on this list. Because every other theory here, every argument about what's real, assumes there's some final level where the truth lives. A place where reality actually is what it is. If there's no bottom, then that place doesn't exist. The truth doesn't sit at the base of the tower. There is no base, just an endless staircase down into smaller and smaller rooms, and no matter how far you descend, another door. And nobody, in all of physics, can tell you whether it ever ends. Number 10. Physics has no equation for the fact that you're experiencing this. We've torn through 9 theories about the nature of reality, and this whole time there's been one fact so close to you that you never turn to look at it. You are experiencing all of this. Right now. There is something it is like to be you, sitting there, these words arriving in your awareness, and that the most obvious fact in your entire existence is the one thing physics cannot explain at all. A philosopher named David Chalmers gave it a name in 1995, the hard problem of consciousness. And he drew a line that still hasn't been crossed. The easy problems, he said, and they're not really easy, are things like how the brain processes light, stores memories, steers attention. Those are just machinery. Hard as it is, we can imagine mapping every wire. That's physics doing its job. But then there's the other problem. Why is any of that machinery accompanied by an inner experience? Why isn't your brain just a very good computer, sorting inputs and firing outputs in total darkness with nobody home? There's no reason it should feel like anything. And yet it does. You're proof. The redness of red, the ache of a sound, the sheer fact of the lights being on inside you. Nothing in any equation of physics predicts that, requires it, or even mentions it. And here's why it's the deepest problem of all. Physics describes the world from the outside. It measures, it weighs, it maps behavior, all of it public, all of it third person. But your experience is the one thing in the universe you can only reach from the inside. It's private. It never shows up on any instrument. You could scan a brain down to the last atom, know exactly what every cell is doing, and still nothing in that scan would tell you that the person is feeling anything at all. So step back and look at where this video landed. We started with 2 rulebooks that can't agree about space and time and the very small. We ended with the fact that the thing reading this sentence, the awareness holding these words, is more certain to you than any galaxy, any particle, any theory. And it's the single phenomenon our physics has no way to touch. You are the best attested thing in existence. You're also the least explained. Physics can weigh a galaxy and time an atom as it collapses. But the one reading this, the one experiencing it, is the measurement it has never once been able to take. It has mapped the whole universe and left out the only part that's looking back.